Hello everyone and welcome to another video. Today I'd like to continue our discussion on ordinary differential equations. So if you've been following along, you've seen we've gotten a lot of good experience with ODEs. We've looked at solving ODEs using the Laplace technique as well as the quote-unquote traditional way of solving them using things like the method of undetermined coefficients. Now that we've got a good bit of experience with specific problems in ODEs, I think it might be time to start thinking about generalizing or standardizing our approach to ODEs. So that's the topic of today's discussion. Is I would like to look at second order ODEs in what are called quote-unquote standard form. Okay, so to set the stage for this, I always like to look at concrete examples. So let's look at our good old friend, the mass spring damper, which again, you guys at this point are probably well familiar with, so I don't need to really go into detail about it, right? Basically, it's a mass, we got a spring, we've got a viscous damper on this guy, and now we need to start asking, can we predict the behavior of this based on these parameters K and B, right? And you know that you should be able to do that. We know that, for example, if B is small, right? If the damping ratio is small relative to the spring constant, we know that the general feeling should be, there should probably be a lot of oscillations in this system, right? It's going to act very springy, right? So this is a case which is typically referred to as an underdamped system. The other alternative is like, let's think of a situation B. What if B was large relative to K? So you've got a really big, powerful damper and a kind of a wussy spring, right? So it's almost like this whole thing is like plopped into honey or something like that. Well, in that case, you know that what should probably happen is there probably won't be any oscillations. This spring is, the system is just going to go like we said, like it's stuck in honey, right? That's a situation which is sometimes referred to as an overdamped system. Finally, the last thing you could maybe do is what if B and K, what if these two constants were a quote-unquote, in balance, or they had a good trade-off, right? In that case, we would probably expect a reasonable response with little or no oscillations. That's sometimes referred to as a critically damped system, okay? So we know just from a gut feeling that these are sort of the three regimes of operation that we expect this system to be in. Can we standardize that and then predict that based on standard parameters, which we're going to see in a second, okay? So the way to go about doing this, I think, is let's go ahead and write down equations of motion again for this specific system and see what type of a differential equation falls out, okay? So let's go ahead and do that. So to do that, let's just go ahead and make ourselves a good old free body diagram. So what's going on with this guy? So you deflected a positive distance x, you've got a spring force that goes back like this, right? So this is kx, and then you've got a force due to the damper, right, which is B times x dot, right? And that's kind of what we've got here, okay? So that's pretty simple. Let's assume that there's no forces on this, and let's just look at the autonomous response. So let's go ahead and write our good old friend equations of motion, which is our buddy Newton, right? F is equal to ma. Right, that's what we're looking at. So what are all the forces on this? Well, we got the spring force, right, which is minus kx, right, because it's all acting in the negative direction, minus the damper, which is bx dot, is equal to the mass times the acceleration, which is just x double dot of t, right? Okay, great. So you put this guy together, you can get this all on one side. So we got mx double dot of t plus bx dot of t plus kx of t is equal to 0, right? You can normalize this. Let's write this. Let's divide through by mass. So let's write this as x double dot of t plus b over mx dot of t plus k over mx of t is equal to 0, okay? So at this point, again, this is the differential equation for this specific system. I don't want to look at specific systems any longer. I want to look at a standardized way of looking at second order differential equations, okay? So the way that is going to happen is we want to massage this to look like x double dot of t plus 2 times zeta times omega n x dot of t plus omega n squared x of t is equal to 0. So this right here that we're boxing up is the standard form of a second order differential equation, okay? You always want to try to write it in this format, okay? So in this case, what you see is this zeta variable. This is referred to as your damping ratio, okay? And this omega n is referred to as the natural frequency of the system. And we're going to see why these things are called those in a second, all right? So in our specific case, we can easily see how are the damping ratio and natural frequency related to these constants K, B, and M, right? So for our case, all we need to do here is basically solve and say we need the coefficient of x dot to equal the coefficient of x dot. So in other words, we need b over m to equal 2 times zeta times omega n, right? And then we need the coefficient of x to equal the coefficient of x. So we need k over m to be equal to omega n squared, okay? So here is two equations and two unknowns, right? We are basically looking for the unknowns, solve this thing for zeta and omega n, right? That's the game plan, solve these simultaneously. That's trivial. I'll let you run over to Mathematica or however you like to do this, and you'll basically end up with, in this case of the mass spring damper, the natural frequency is square root of k over m. I mean, heck, you can see that right here, right? Just solve this for omega n, just take the square root. Then you take this result, jam it into this other equation, and you're going to get that the damping ratio of this guy is b all over the 2 times square root of km. Okay? So that's what you're going to end up with. Okay? So, okay, at this point, what we want to do is we almost want to just sit here and throw away K, B, and M. Because, again, those were constants for this specific mass spring system. We want to start playing with now zeta and omega n. I only want to focus on this standard second order differential equation, right? So, again, maybe we ought to label this, right? This here is the standard form second order ODE, right? Anytime you see a second order ODE, the first thing you want to think about is always just massage it to get into that form, similar to what we've done here, okay? All right, so the next thing we want to do is, well, tell you what, actually, give me a second. We ran out of whiteboard space. I'll pause the camera, erase the board, and we'll be back in a second. All right, so I've just moved our standard second order ODE up here, and now let's go ahead and start thinking about how we're going to solve this, right? Again, how are we going to find x of t? Again, hopefully you watched our discussion here on the Laplace transform, because that's exactly the way I want to solve this. So let's just Laplace transform both sides of this. So here we go, Laplace transform x double dot. So that is what? It's going to be s squared x of s, right, minus s times the initial position of the block minus the initial velocity, right? That's this first term. Okay, this plus, okay, we got to do this 2 times, whoops, that looks like a zeta. Got a little bit over eager there. 2 times zeta times omega n times Laplace transform of this guy, right? Again, that is s times x of s, right, minus the initial position of the block, right, in the time domain. That's this whole term. Now, finally, this one plus omega n squared, and then all we end up with is x of s is equal to 0. Great. Okay, so now we got an algebra problem. Solve this sucker for x of s. I'm gonna skip the boring steps. Feel free to run to Mathematica and do that if you like. Why don't you just take my word for it that if you do this properly and work the algebra out, you get something like this. This is going to be s. I'm going to call this x0. I'm going to change notation slightly. Let's call this x at times 0. Let's call this thing x0, and let's call this guy right here x dot 0. It's just the initial condition, right? Similarly, this guy over here, let's call this thing x0, right? That's what we're doing. Okay, so you get s x0 plus x dot 0, right? Plus 2 times x naught, or x0 zeta omega n, all over s squared plus 2 zeta omega n s plus omega n squared. Okay, great. So here's what a standard second order ODE is going to do in the Laplace domain, right? So you see, again, our characteristic equation shows up, right? S squared plus 2 zeta omega n s plus omega n, which exactly looks like this differential equation as we expect. And then the zeros of this polynomial just kind of mix and match depending on the initial conditions, right? So what's interesting here is, okay, the next thing you're going to want to do, right, is we are going to want to solve for the roots of this characteristic equation, right? So we understand what the behavior is going to be like. So you look at this, this is just a second order polynomial, right? So how do you find roots of a second order polynomial? Well, you just go to the quadratic equation, right? So the roots of this thing right? This is going to be, what's a quadratic equation, right? It's minus b plus or minus square root of b squared minus 4ac all over 2a. Right? So in this case, the b, right, is the coefficient of this of the linear term, right? So it's this thing. It's 2 zeta omega n. So we end up with negative 2 zeta omega n, right? That's the b, plus or minus the square root of b squared. So I got to do this here. So let's be a little bit careful. So this is 2 zeta omega n. This is the b squared minus 4 times a, right, which was the coefficient of the squared. Well, good, that's a 1. 4 times 1 times c, which was the constant here. So it's this, oh, sorry, I'm pointing at the wrong thing. Times omega n squared, right? So this guy here is just omega n squared all over 2a, right? So that's just 2 times 1. Great, okay, so you massage this guy around a little bit, and you end up with, again, we're finding roots, right, of the characterize equation are basically minus 2 zeta omega n plus or minus the square root of, you massage this sucker around a little bit, and you basically, well, I'll tell you what, let's leave it like this. How about 2 zeta omega n squared minus 4 omega n squared, right? Like that, all over 2. Right? Okay, so now you got to ask yourself the question, what do these roots potentially look like? So we end up with kind of 3 cases. Case 1, right? What could happen is this discriminant right here, right? The b squared minus 4ac term, if all this gobbledygook, by the time you plug in the zeta and omega n, if this comes out to be strictly positive, that means this is a real number, right? There's no imaginary component. If the discriminant is positive, so let's write that down. If this thing 2 zeta omega n squared minus 4 omega n squared, if this is strictly greater than 0, right? If it's positive, what happens? Well, we're going to see that, again, this is real. So maybe what we should say is, what happens if this is true, then we end up with distinct real roots, right? Wouldn't you agree? Because this thing, the discriminant is positive, so by the time you take the square root of a positive number, you end up with another positive number, a positive real number. So the roots are something plus a real number and something minus a real number. So they're going to be different, right? So you're going to have distinct real roots, right? So let's stare at this longer. If this is true, what ends up happening? And this is why this is so great being in second order form. Let's expand this a little bit more. Okay, so over here, what is this? This is 4 zeta squared omega n squared minus 4 omega n squared is going to be strictly greater than 0, right? Okay, so actually, check this out. Can't I pull out 4 times omega n squared on this? So we end up with zeta squared minus 1. It's got to be greater than 0. Great, okay. So this thing is positive, right? I don't care what you end up with omega n. 4 times omega n squared, this is positive, so I can divide both sides by 4 omega n squared, right? And I'm not going to flip the sign of this inequality, so I end up with zeta squared minus 1 is greater than 0, right? So again, greater than 0, right? Move this to the other side, so I end up with zeta squared has got to be strictly greater than 1, right? So actually, you could even yeah, I guess we could take the square root if you want. So this is basically zeta is greater than 1, right? So here's the condition that if zeta is greater than, if the damping ratio is greater than 1, you end up with this case of distinct real roots. And again, this is sort of the overdamped situation, right? Because we know from our previous discussion on differential equations that if you have distinct real roots, the solutions are going to look like e to the r1t, e to the r2t, right? So there's no cosines or sines or anything like that in it. It's going to be strictly overdamped, right? You're only going to have exponential behavior. So this is interesting, right? So what's so cool about standard second order form differential equations is this thing zeta, this damping ratio, tells you all that right off the bat. The second you know zeta, you just check, is it greater than 1? If it's greater than 1, awesome. You've got distinct real roots, you've got an overdamped case. So that's almost like, here, where do we have this? Crud, I shouldn't have done it like this. But, right, here we go. Bam, right? overdamped, right? So damping ratio tells you everything, right? Okay, let's look at another case. What if it wasn't the, let's look at maybe a case 2. And I know you can't probably do this easily in your notes, so you might hate me about this, but let's say case 2 is, what would happen if this discriminant was exactly equal to 1, right? Or sorry, if exactly equal to 0. Well, if this discriminant here is equal to 0, you see what we're going to end up with is this whole thing is going to be 0. So we're actually going to end up with what? We're going to end up with repeated real roots, right? And again, you can flow through this entire discussion, right? So again, this is now an equals 0, right? And this is, again, this is now becomes an equals 0, this becomes an equals 0, this becomes an equals 1, this becomes an equals 1. So, aha! Here, we end up with, if zeta is equal to 1, you have repeated real roots, and you actually end up with what is referred to as critically damped. And again, I'm going to put a big asterisk on this. We're going to come back to this discussion of critically damped. In this definition here, you see that if zeta is equal to exactly 1, if zeta is unity, if your damping ratio is unity, we end up with repeated real roots, which some people refer to as critically damped. I'm just going to throw it out right there that other controls engineers that you may run into, they may refer to zeta as 1 over root 2 or 0.707 as being critically damped. So you just got to be careful on your nomenclature. From a mathematical perspective, from the roots, it's actually when the damping ratio is 1. From a performance perspective, some people may like this value of damping ratio better than this, and they might call this critically damped. So again, I hope I haven't confused you, but just be careful who you're talking to in the nomenclature you're using when you throw around this term critically damped, okay? So for our discussions today, let's just say damping ratio of unity means critically damped. And again, you see what that ends up with is, you know, now this arrow should probably go down here, right? So case 2 is you got this situation, right? And again, the beauty of this standard second order form is that the damping ratio tells you all of that right off the bat. Let's finish our discussion then. The last thing, you could end up with a case 3, right? What if this this term, discriminant, what if it's strictly negative? What if it's negative? Well, if that's negative, you see we got a, this is where it gets interesting. Maybe I shouldn't call it a problem. Because if this is negative, the discriminant is negative, you take the square root of a negative number, this junk here becomes an imaginary number. So you see that in that case, if it's negative, you actually now have the case where you have complex roots, right? Right? And again, we let's keep doing it. Let's do this. Let's change this to a less than, to a less than, to a less than, to a less than, and to a less than. So again, beautiful. The damping ratio, if your damping ratio is less than unity, you end up with complex roots, which is sometimes now again referred to as underdamped. And again, we come up with, here we go, case 3 explains this situation where it is underdamped. So again, the beauty of this here is we saw that it all boils down to this damping ratio. This is exactly why you want to write your second order differential equation in this standard form, because if you write it in the standard form, the second you compute the damping ratio zeta, you know which one of these 3 cases you're in, and we can take appropriate action, okay? So let's go through the 3 cases, the overdamped, the critically damped, and the underdamped cases, and see what does the solutions look like if we are talking about using zeta and omega n for our differential equation. All right, so let's look at case 1, the overdamped situation when your damping ratio is strictly greater than 1. So again, here was what x of s was, again, for any second order standard differential equation, right? This could be either case 1, 2, or 3, and we also showed that the roots for any of those cases were given by this expression, right? Which was basically quadratic equations solving this bottom. Let's clean this guy up actually just a little bit, because you can see it's a little bit redundant. You could factor out like a 2 and an omega n. I think you can kind of pull it out. I think if you stare at this long enough, everyone would agree that this is the same thing as what? It's minus 2 zeta omega n plus or minus, let me see, this should be 2 omega n on the outside and then square root of zeta squared minus 1 on the inside of the radical all over 2, I think, right? So these 2's will all cancel out. So really the roots, you could write this as minus zeta omega n plus or minus omega n square root of zeta squared minus 1, okay? So this is a slightly more helpful form of the roots. Maybe let's do it like this. This is our roots R1 and R2. Right? And actually here, tell you what, let's do this. Let's box it up like this and erase this junk in the middle. That's the other way we could get at it, right? Okay, so here we go. Here's what it does. Here's the roots of the system. And now let's go take a look at case 1. Okay, so case 1, we saw that in this case, these roots here, they're going to be distinct and real, all right? Because since zeta is greater than 1, you take zeta squared minus 1. Again, this thing, this radical is positive, so we end up with basically a bunch of positive numbers here, right? Or sorry, not positive, but real numbers, right? Okay, so in that case, what we're gonna wanna do is we can take this and we know the type of partial fraction expansion that is going to work, right? So again, make sure you watched our discussion on the Laplace technique, doing the partial fraction expansion and the inverse Laplace transform, all of that kind of stuff, because we wanna get this thing in the time domain. So I know that x of s in the Laplace domain looks like this. So in other words, let's just say here, well, I'll tell you what, I'll rewrite it. So sx0 plus x dot 0 plus 2x0 zeta omega n all over s squared plus 2 zeta omega n s plus omega n, right? So we know that since I know in this case, the roots of this are distinct real roots, we can try a partial fraction expansion of the form some coefficient a1 all over s plus root 1, right, plus a2 all over s plus root 2, right, where root 1 and root 2 are given by this right here, right? Okay, so again, this is a little bit boring because at this point, this is just, I'll say dot, 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 do the partial fraction expansion of this, right? And again, we talked about how to do that in a previous video, so I don't think it's worth going over it. Instead, what I will give you is that A1 coefficient, right? By the time you do this math, A1 is going to look like, oh gosh, this thing is not pretty, but it's definitely doable in a symbolic manipulator. So negative x dot 0 plus x0 times the quantity negative zeta omega n plus square root of zeta squared minus 1 times omega n squared. All this is underneath the radical like such. N parentheses here, this is the numerator, and then the denominator looks like 2 times radical of zeta squared minus 1 times omega n squared. Okay, yuck. Whatever, you can do that though, no problem. And similarly, A2 is going to look kind of just as ugly. So this is positive x dot 0 plus x0 times the quantity zeta omega n plus square root of zeta squared minus 1 times omega n. This is the numerator all over 2 times radical of zeta squared minus 1 omega n squared. Okay, yuck. Okay, that's fine. They're ugly constants, but at the end of the day, they're just numbers, right? You plug in all these numbers for your initial conditions, your damping ratio, your natural frequency, you come up with 2 numbers, right? Because that's what these 2 things are. They're coefficients. Same thing with the roots. The roots are just numbers. So at this point, you can basically see that the inverse Laplace transform of these 2 terms, they're just exponentials, right? So we get what we're looking for of x in the time domain, right? It's just inverse Laplace transform these things, right? So this is just a1 e to the minus r1t plus a2 e to the minus r2t, right? which we have right here. We got everything. Again, I'm not going to plug in all of those because you see A1 is ugly, A2 is ugly, root 1 is quasi-ugly, root 2 is quasi-ugly, but they're all doable, right? So we end up with, here's the response of the system, right? And what we can then show is that this satisfies the original differential equation and satisfies the initial conditions. Again, maybe in the interest of the time, I'm just going to flash up a screenshot of me doing this in Mathematica to prove to you that I'm not jerking your chain, that if you actually do plug these in, this solution here will satisfy x double dot of t plus 2 zeta omega n x dot of t plus omega n squared x of t is equal to 0. That will come out correctly, and x at time 0 is going to equal x0, and its derivative at time 0 is going to equal the specified initial condition here. So again, here's the Mathematica screenshot showing that all of this checks out. And in fact, here I'll show you also the plot of what this function looks like. But as you can see, it's just the sum of two exponentials here. So again, this is great because with our standard second order form, the second you see your damping ratio is greater than 1, you know the solutions are just the sum of exponentials here, right? No oscillations are possible. Okay. Great, let's move on to now case number 2. All right, so moving on to case number 2, what if you have a critically damped system, right? What if zeta is exactly equal to 1? So, well, maybe tell you what, let's come over here and look at our roots. What happens if zeta is exactly equal to 1, right? So you have roots 1 and 2 is equal to, well, I guess it's negative omega n, right? Plus or minus omega n times square root of 1 squared minus 1. So this is all gone. So you actually end up with, as we see 2 repeated roots at s is equal to negative omega n, right? So there's 2 roots there. Okay, so great. So we see this sucker down here has 2 roots at s is equal to minus omega n. So it's repeated. So we basically know that this entire junk, right, this x of s, just like we did last time in the case 1 case, is we want a partial fraction expansion this guy, but now we know that the appropriate partial fraction expansion to take is now a1 all over, well, where's the first root? It's s plus omega n, right? So here's the root at minus omega, s equals minus omega n, plus an a2 all over s plus omega n squared. So again, remember, watch our video on partial fraction expansion so we can understand why this one's got a squared and this one doesn't. Again, this is just because we have repeated roots, right? So we need to take a different form of the partial fraction expansion. So again, you go ahead and you walk your way through this thing, and you go ahead and get these coefficients a1 and a2. So I'm going to say dot 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 here. Again, this is do the partial fraction expansion. You're going to get a1. This is not so bad in this case. a1 turns out to be actually just x0, and a2 turns out to be x dot 0 plus x0 omega n. Great. Okay, so you just plug that in, and again, you do the partial fraction expansion and the inverse Laplace transform, and we end up with x of t, in this case, is just going to be, come on, where is it? I wrote it down here. Yeah, here. So it's just x0 e to the minus omega n t. Yeah, that's the first one. Right. Plus t e to the minus omega n t times, we've got a scaling factor here of x dot 0 plus x0 omega n. Great. Great. Okay, so here is our solution. Here. And again, we see no real oscillations, right? You might have a slight bump due to this t growing while this is decaying, but again, we can show that this thing solves the differential equation, solves the initial conditions, and we can plot it. Again, here's another screenshot of me doing this in Mathematica to show you that this is the solution for our case 2 situation. Okay, so that one wasn't so bad. Let's do the last case, which is where things get interesting. All right, so the last situation, case 3, is where we have an underdamped system. So if your damping ratio is strictly less than 1, let's take a gander here at what the roots look like. So in this case, roots 1 and 2, right? It's minus zeta omega n plus or minus omega n times square root of this thing here. Now, since zeta is less than 1, you square it, you get something again, less than 1, so you get something less than 1 minus 1. So the thing under the radical is negative, so this entire thing becomes imaginary, right? So maybe an other way to look at this is you could also think about this is let's flip this. Let's put a minus 1. In other words, here, tell you what, let me write it like this. How about minus 1 minus zeta squared? Would everyone agree that's the exact same thing? I haven't done anything to it, right? The only thing that I've done here is maybe here, let's write it like this. How about minus 1 times that? That's the exact same thing, right? Or I could write this as, how about minus zeta omega n plus or minus omega n times, let me do this first part here. How about the 1 minus zeta squared times square root of minus 1? Would everyone agree that's the exact same thing? All right, I haven't done anything. Now this, you remember, that's I, right? This is the imaginary number, so I end up with minus zeta omega n plus or minus omega n times square root of 1 minus zeta squared times I, right? Now, again, we know, let's make a note here, that zeta is less than 1. So now this term right here, right? Maybe let me put the implication like this. So 1 minus zeta squared, right? Again, we know zeta is less than 1, so I square it, I get something less than 1. So 1 minus this whole thing, this term is positive, right? So therefore, this thing, this term square root of 1 minus zeta squared, in this case, this is a real number, right? It's not an imaginary number, it's a real number, okay? So we end up with, if you look at this long enough, it's basically, here's your real component, here's the imaginary component, right? Let's call this real component this thing, how about like sigma, or something like that, and let's call this imaginary component omega d. Right? So what I'm getting at here is you could write the roots if you wanted to in this particular case of, it's basically negative sigma plus or minus omega di, right? Where sigma is going to be the product of the damping ratio times the natural frequency, and this omega d is going to be this thing omega n square root of 1 minus zeta squared, okay? We're going to come back to this in a second. I just wanted to point this out, okay? Okay, so tell you what, now that we kind of understand what the roots look like, and maybe, heck, we could even plot this on the real imaginary axis, right? So there's going to be 2 roots. We know they're going to have a real component, which is this sigma term, right? So sigma is the real component here, and you're going to have an imaginary component, omega d, right? So here's root 1, here's root 2, right? That's what this is going to look like. Okay, all right. So let's go back and do like we were doing again. Let's go ahead and try to find the partial fraction expansion of this thing when we understand that the roots of this guy are given by a pair of complex conjugates, right? Okay, so the way we're going to do that is first, tell you what, sorry, maybe I jumped the gun here. Let's go ahead and rewrite the denominator here. So we're going to try to complete the squares. We're going to need to do that to do our partial fraction expansion. So let's go ahead and first rewrite the characteristic equation, or basically this denominator, right? So I would like to take this thing, s squared plus 2 zeta omega n s plus omega n, right? That's the denominator. I want to rewrite this thing as basically something that looks like an s plus alpha squared plus omega squared, right? This is what we're going to want to rewrite it in an alternate form. So you could do this easily. I guess maybe the easier intermediate step would be, let's call this thing s squared plus, let's put this whole gobbledygook, the coefficient of s, let's call that just some other constant. This is all this gobbledygook, let's call it d. So let's call this thing ds, and then let's call this constant over here, well, I guess we can just leave it as omega n, or sorry, let's call this e. Let's call this thing e. Again, that's kind of a dumb substitution, but I just want to write this as squared plus constant s plus constant, right? Okay, so let's see. If we now equate this to this side, right, so s plus alpha squared plus omega squared, right, you can basically find out what are s, or what are alpha and omega in terms of zeta and omega n, right? So what we end up with here is alpha is going to be zeta times omega n, and this omega term, right, in our completing the squares, is going to be square root of 1 minus zeta squared and omega n squared, like this, okay? So that's what we end up with, and again, let's go ahead and recall that zeta is strictly less than 1 in this case. So this is less than 1, so actually, so this entire thing is positive, right? So the implication here is this omega, right? This is going to be a real number, right? It's not an imaginary number, right? Okay, so if that's the case, what we can do is we can now go ahead and complete our partial fraction expansion by completing the squares like we did here. So we're basically going to take this entire thing here. I tell you what, I'm going to cheat since this is our last case. We want to rewrite this guy using partial fraction expansion in a slightly different format. We want to write this guy as again, we're rewriting the denominator to look like s plus alpha squared plus omega squared, right? And we just showed you could do that. Let's leave the numerator the same thing, right? So this is going to be, yeah, sx0 plus x dot 0 plus 2x naught zeta omega n, right? Is that the same thing? Let me make sure I got my notes right. Yeah, yada, yada, yada. Yep. Okay, so now, again, it's just manipulating this side to get it into a form that's inverse Laplace transformable. So I'm torn if I want to actually go through this and waste your time, because it really is just algebra at this point. Yeah, tell you what. It's in the lecture notes. If you want to see this, feel free to look at my lecture notes. We basically, let's do 1 or 2 steps, okay? Let's do 1 or 2 manipulations, okay? Let's rewrite the numerator up here as, I'm going to divide through by x0. So I can write this guy as s plus, where do I have this sucker? Yeah, here, x dot 0 all over x0 plus 2 zeta omega n. Yeah, did I get that right? Yeah, that's right. Okay, all over, sorry, yeah, no, I'm not, let's pull out that x0 out here. So this is, okay, so all I did is just pull this x0 out of the numerator. So the denominator is the same. I'm just gonna write this thing as same. It's this guy, okay? All right, so now, at this point, what we could do is we could add and subtract the term x dot 0 over x0 plus 1 zeta omega n. We can add that and subtract it from the top. So in other words, let's do this. I'll do one more step. Okay, so we got this whole junk all over same. You got x0 hanging out here. Let's rewrite this thing. So this is s plus x dot 0 all over x0 plus 2 zeta omega n, right? This, haven't done anything, okay? Now what I'm going to do is I'm going to add and subtract the same term from the top. So what we're going to do is, let's go ahead and subtract first. Subtract x dot 0 all over x0 plus zeta omega n, right? And then I'm going to have to add that exact same term, and I ran out of space. Let's move this over. Plus x dot 0 all over x0 plus zeta omega n, right? Now, that might look a little dumb because, like, why have you even done that? But I've done this because we can combine these terms here, okay? So the last thing that we end up with is you can massage this guy at this point. You massage it all the way down to look like s plus zeta omega n plus plus yeah, okay, x dot 0 all over x0 plus zeta omega n, right? You can look like that all over, oh sorry, and we got to put this in parentheses, right? x0 is still hanging out here. Okay, all over s plus alpha, and actually we have alpha, right? Alpha was zeta omega n, so is s plus zeta omega n squared plus, what was omega? Omega was that thingy over there, right? All over, oh, well, I'll tell you what, let's leave this as, I guess in my notes I left it as omega squared, okay? Okay, so now what we can do is we can break this up into 2 forms that look reasonable. So we can, let's do this over here. Okay, so the last part of this partial fraction expansion, and again, we're just going over this one in a little bit more detail because it's a little more involved here, but you could basically get this guy. Let's bring this over. So this is going to equal, you can get this thing to look like s plus zeta omega n all over s plus zeta omega n squared plus omega squared plus x dot 0 all over x0 plus zeta omega n all over s plus zeta omega n squared plus omega squared. And then this whole thing, all of this is multiplied by x0, right? We still got this x0 hanging around. Okay, the reason why we did all that manipulation is because now this is a form that's inverse Laplace transformable. This is a form that's easily recognized as an inverse Laplace transform. So if you do this, now I'm gonna dot 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 and skip some of these steps, but now do inverse Laplace transform. Right? And this is basically sinusoids, right? Sinusoids pre-multiplied by an exponent, right? So we end up with, at the end of the day, doing the inverse Laplace transform to get x of t, right, in the time domain. This thing is going to look like x0 e to the minus alpha t cosine omega t plus another ugly constant here, x dot 0 minus x0 zeta omega n all over omega e to the minus alpha t sine omega t. Yuck. Okay, and again, there's still some substitutions that you could do. We know what alpha and omega are. You can plug this in, but all you end up with at the end of the day here, right? This x of t, whoops, x of t, doesn't this just look like basically it's some constant? So it's like, you can call this thing a constant if you, or well, it's not really a constant because it's an exponent. Let's call this thing a. Let's call this junk here b, right? This thing looks like an a cosine omega t plus b sine omega t. Obviously, with the understanding this a and b, they're an exponentially decreasing term here, right? So this is pretty awesome. Let's go ahead and give me a second to pause and erase some of the board, because let's rewrite this in a slightly more useful format. All right, so here's where we left off. Again, notice that this thing is basically, it's a cosine and a sine wave added together, and furthermore, the coefficient here, both of them have this e to the minus alpha t, right? So you know what, we could actually pull that out. So tell you what, let's write this guy as x of t is just, let's yank out this e to the minus alpha t here, and we would end up with, I think this would just end up with x0, right, cosine omega t plus x dot 0 plus x0 zeta omega n all over omega, right, sine omega t, right? I think that seems reasonable. And now this is, we can get even more fancy with this, because if you look at that long enough, right, we can basically take another look at this, and you gander at this thing and you can say, all right, this is basically e to the minus alpha t, right? There's this decaying exponential in front of this, and this thing inside, again, I hate to use this nomenclature, but oh gosh, I'm running out of symbols. Fine, let's call this a tilde cosine omega t. Well, actually, no, not even omega t. Like this, it's both the same. Let's call this a tilde cosine of z, right, plus b tilde sine of z, right? Would everyone agree that's like, this is basically what it looks like when you boil it down to it. Now, we can use a trig identity on just this part here, where we can recognize these are two, it's a cosine and a sine wave at the exact same angular frequency. They just have different coefficients. You're adding them together. We should get a single sinusoid out of this. So what I want to do here is I want to apply the trig identity where we're going to basically say that a tilde, right, a tilde cosine of z plus b tilde sine of z. This is just a single cosine wave, right, of magnitude capital A cosine of z, and then minus a phase shift. Let's call that phi here. So in this case here, this big A, it's nothing more than, if you look up your trig identity, A is just square root of A tilde squared plus B tilde squared, and this phase shift phi is basically the inverse tangent of, where did I have this thing? I keep losing it here on the page. Oh, here, B tilde all over A tilde. And actually, this is probably not a good way to go. I would recommend using the 4-quadrant inverse tangent. Again, we had another video discussing why a single tangent like this is a bad idea, and the 4-quadrant is the way to go. So I'll leave a link to that in the description, or click on the card that's flashing in the upper right of the screen. So I would do something like A tan 2 of B, let me see if this is y. Yeah, B tilde, A tilde. Again, you got to remember that this is the A tan 2 function, which expects the y component first and then the x component, right? Okay, cool beans. All right, so gosh, plug this in. We have all these. We know what A tilde is, right? A tilde is just that. B tilde is just this. We know what Z is. It's this omega t, and unfortunately we got to go back again. Omega is over here. We've got everything. Everything can be written in terms of the damping ratio and the natural frequency. So you do all this, you plug all that trig identity in, and then finally what we end up with here is the solution to this system is, tell you what, where am I going to have some room? Let's come over here. Let me erase this. Yeah. Okay, let me erase this because this is what we're gunning for right here. The solution for this standard second order underdamped situation is nothing more than A e to the minus zeta omega n t times cosine of, let's call it omega d t minus phi, where all of these constants, this big constant A, capital A, it's something, it's a number, but it's a little bit ugly, but it's your initial position squared plus the quantity, the numerator is x dot 0 plus x0 zeta omega n. This thing is all squared, all over 1 minus zeta squared omega n squared. Okay, that's this A. Okay, omega d, all right, omega d is going to be omega n times square root of 1 minus zeta squared. And finally, this phase shift phi is A tan 2 of B tilde and A. So this guy, the y component was x dot 0 plus x0 zeta omega n all over omega n square root 1 minus zeta squared. Okay, so that was the y component, and then the x component is just x0. Yikes here. Okay, so then again, this is the y component, and this is the x component of your A tan 2. Okay, great. We better box that up because, man, we spent a lot of time getting to this, and this is the important part. Right, box this up because this thing in red is basically the solution of your standard second order differential equation when you have an underdamped system, right? Again, this is valid when zeta is strictly less than 1. And let's take finally a moment to step back and interpret this and maybe provide a little exposition and discussion on this, right? Because what we see here is the beauty, again, of standard second order form is this is true for any standard second order form system. You massage it, it's a mass spring damper, a pendulum, a fluid flow problem, whatever. As long as you get the damping ratio and the natural frequency, this is the solution to that differential equation, right? And we see it's nothing more than an exponentially decaying sinusoid, right? And maybe we should write that down, right? So solution is a sine wave, or, well, I guess a cosine wave, however you want to interpret that, right, with a exponential decay, right? Or I guess, or growth, depending on the sign, S-I-G-N of that term. But all this thing looks like, right, it has to look like something like this. Again, I'm going to assume that the natural frequency and the damping ratio are both positive here, okay? Beautiful. What else is beautiful about this? If you look at this long enough, you see that the angular frequency of this, the speed of oscillation, right? The angular frequency of the oscillation, it is not the natural frequency. We better write that down, because this is probably the very common problem that, or misconception that I think a lot of people have with second order systems. They hear the term natural frequency and they think, oh, that must be the frequency at which this system oscillates. No, that is not true. The system oscillates at what? You can see it right here. It oscillates at omega d, right? Which is actually omega n times square root of 1 minus zeta squared. So this is sometimes referred to as the damped natural frequency, right? And you can clearly see from this expression, right? This is the frequency at which this system oscillates. It's the damped natural frequency, which is close to the natural frequency, right? If zeta is small. But if your damping ratio goes up, this frequency that it oscillates at can be very different than your natural frequency. So again, just be a little bit careful about that, right? Yeah, what else is interesting to discuss about this? Let's come back to that thing we talked about where, in this case, we have zeta, which is less than 1, okay? This is what we call underdamped. But some people will want their system to have a damping ratio of 0.707, which is 1 over root 2, right? This is desirable. Because what it allows you to do is it's this kind of good trade-off where the system, sure, it might oscillate a teeny little bit, but it's going to respond fairly quickly, okay? So a lot of times people like to shoot for a damping ratio. If you can make your system by tuning the springs or the dampers or the length of the pendulum or whatever, if you can make your damping ratio about 0.707, they give you a thumbs up and they say that's great. Some people confusingly call this critically damped. I don't like this notation because I like to think about critically damped as when you have a damping ratio of exactly equal to 1. But again, whoever you're talking to, just make sure you know that we're all on the same page, right? Okay, so great. This is pretty awesome. It looks like it's working. Tell you what, this I think is so important that I think we should maybe go to Mathematica and prove to ourselves that this solves the differential equation and the initial conditions and we're not jerking your chain. So maybe let's go do that real quick.
All right, so let's verify that what we had on the board is actually correct. So again, here's the constant A, here's the damped natural frequency, and here is that phase shift that we were talking about. Again, the only thing I want to call out here is since I'm using Mathematica, when I use the 4-quadrant inverse tangent, it expects the x component to go in as the first argument and then the y component as the second argument. So that's why this might look a little slightly backwards from what we had on the board, because on the board I was using kind of the assumption that the 4-quadrant inverse tangent that you're using would take y and then x, not the other way around. So anyway, this should be correct. So let's shift enter and get all of that into Mathematica. And now what we can do is let's go ahead and basically just write down / define the solution to the underdamped system, right? So that's this, right? We just had it. It's a e to the minus zeta omega nt times cosine omega dt minus the phase shift. So there we go. Shift enter. Here it is. We claim that this function here will actually go ahead and solve the ODE. So we better do that right now and verify that this solves the ODE. Right? So that is, I got to take the second derivative, so it's x double dot, so let's get x double dot. So that's this, right? That's x double dot plus 2 times zeta times omega n times x dot. So here, let me get x dot. there's x dot, plus omega n squared x of t, right? When I enter this thing, this better equal 0, right? So shift enter and, well, okay, it didn't quite get that because it didn't simplify it. Let's ask it to simplify this and cross our fingers. Yay, look at that. It's true. It works, okay? So this solution, this is the solution to our differential equation. Now, let's check and verify that this satisfies the initial conditions, right? So I better have, when this thing equals 0, this better just say x0, right? So shift enter, yay, that worked. Now let's verify that when I take the thing's derivative, so I think you would agree this is x dot. I need x dot when time is equal to 0. This better equal x dot 0. So shift enter, yay, look at that. This is working. Amazing. This crazy thing is the solution for an underdamped standard second order differential equation. We just proved it to you right here. So now for giggles, let's go ahead and plot this for some representative slash kind of arbitrary, I can't spell this, whatever, you know what I'm saying here, arbitrary zeta omega n, and then also we have got to pick some initial conditions, right? We need to pick some initial values to plot this thing at. So, I don't know, let's make this up. Plot, let's see, sorry, I lost my mouse here. Okay, plot x of t, let's make up some values. Let's say, I don't know, omega n, let's use 2, a damping ratio, we got to pick something smaller than 1. How about 0.3? How about the initial condition? Let's make this negative for giggles. How about -3, and then how about x dot 0? Let's make this -1.5. Again, we're just kind of making stuff up. So let me go ahead and put all of this in parentheses. There we go, and that should be a representative function. Let's plot this function from t equals 0 to 10 seconds. All right, and shift enter that guy, and oh, it cuts some of this thing off. So tell you what, let's change the plot range. Whoops, plot range, all, shift enter. There we go. Now look at this. This looks awesome, right? It looks like the curve that we drew on the board, and look at this. It meets the initial condition. The initial position is 3, and the initial velocity, right? The initial slope here is indeed -1.5. So I think I believe it. I think this works. So let's jump back over to the board and talk a little more about it.
All right, so hopefully we buy that this is the actual solution to the differential equation. So again, we plotted it out here, and this might be interesting to think about because this is a cosine wave, right, which is encompassed or encapsulated by this decaying exponential term here, right? So this thing in dashed, right, this is basically a e to the minus sigma omega nt, right? And the underlying cosine wave is this term here, which we said oscillates at a frequency of omega d, right? So what's interesting now is what if we were to examine, say, successive points, like maybe the easiest part to do is let's look at a maximum of the cosine wave here and then the maximum of the cosine wave over here, right? I think everyone would agree that the frequency obviously between these, here's the angular frequency omega d, so the period between these, right? So the wave is going to basically repeat every 2 pi multiple of this here, right? So in other words, what we're going to say is when omega n square root of 1 minus zeta squared t minus phi, right? That's the argument of the cosine wave, right? When this thing equals 2 pi n, right, for n equals 0, 1, 2, right, some integer value, the cosine wave, it repeats, right? That's what it does. So what's kind of interesting about that is, again, we can ignore this phase shift, right, if we want, because it's just a constant offset. So maybe let's ignore this for now. Right, it won't really matter. The wave is still going to repeat at these times, right? So we basically can look at when is the time when this cosine wave repeats, right? And this is going to be a function of this integer n, right? So basically just solving this, again, using this idea of angular frequency and relating it to the period, I think you'll end up with this is, 2 pi all over omega n square root of 1 minus zeta squared times n, right? So again, for n equals 0, 1, 2, yada, 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 right? At any of these critical times, the cosine wave repeats. So it'll give us those green dots. Those are quote unquote repeating times. Or we could look at, you know, any other time that is similar. So I don't know, like let's say, you know, a third of the way on the downward edge, and then we come here and find a third of the way on the downward edge. Right? Those are quote unquote repeating times, right? They correspond to the same location on the cosine wave, okay? Now, what's fascinating about this is let's look at the ratio of the signals between two of these times, right? So let's define this ratio eta. This is basically the solution here, x, right? This x, but let's look at this at, you know, t repeat of n plus 1 all over x of t repeat at n. Right? So all we're doing here is, again, this numerator is this further along point in time. The denominator is the time one period back, right? So it's either the ratio of this green dot to this green dot or this blue dot to this blue dot. It really doesn't matter as long as they're equivalent locations on the wave. Let's look at what this ratio is. So basically all we want to do is just jam this, right, into our expression for x. And again, we just did this in mathematics, so I don't think I want to do this out on the board. So here's a screenshot of what will happen if you plug that into Mathematica, right? So just take t of 2 pi over omega n square root of 1 minus zeta and then n plus 1, plug it in everywhere you see a t here. That gives you the numerator. Do the same thing for the denominator, but just use an n. And what's fascinating about this is if you do that, again, here's the Mathematica screenshot. What Mathematica is going to tell you is this ratio is going to come out to just turn out to be e to the minus 2 pi zeta all over square root of 1 minus zeta squared. So all of this, again, this is all e to this thing. So here's the ratio. What's fascinating about this is that, look at this. It's only a function of the damping ratio. Again, this is why this damping ratio is so critical in standard second order forms, right? It tells you all this information about the system. So this ratio, omega n doesn't matter. I can have any omega n I want, and if I just examine the ratio of successive points of this wave, this is what you end up with here, right? So the reason this is interesting is this almost kind of helps you start thinking about how you might go about trying to find the damping ratio for a second order system if you don't know it, right? What if you don't even have a model? What if you have an experiment of like a pendulum that's swinging around, right? Well, what you could do then, if I want to know I've got this pendulum system, right, or something, I don't know what the length or the mass, or I can't measure it or whatnot, all I might want to do then is I can measure the angle of the pendulum as it swings back and forth, right? It's going to trace out some kind of curve like this, right? It's going to get this decaying exponential sinusoidal curve, right? And if I want to model this as a second order system, you can think about how can I go about finding the damping ratio of this? Well, we can make use of this fact that the ratio of any two points on the curve are related to eta, are only related to the damping ratio. So what I would do is pick any 2 points on this curve that are, you know, one period apart. Again, probably the easiest thing to do is 2 maximums or 2 minimums. Heck, let's take 2 minimums. You take this point and you take this point, right? You measure, you know, the values, right? So here's val 2 and here's val 1. Value 1, 2, and 1, right? So eta, right? We said that this eta, this is just basically it's val 2 divided by val 1. So you can get this experimentally. This is going to come out to be some number, right? And you know now that basically it's related to the damping ratio through this. So say you come up with this number, and you can say, oh, I know that has to be equal to e to the minus 2 pi zeta all over square root of 1 minus zeta squared. Solve this thing for zeta. This is going to pop out the damping ratio that you can obtain experimentally. So incredibly powerful, lots of fun. You can get lots of information out of this second order system by just kind of inspecting it, right? Okay, So, yeah, that's great. All right, give me a second to erase the board, and let's talk now about a different, a related topic. All right, so I'd like to quickly talk a little bit about how the damping ratio and natural frequency are related to root location. So again, this was sort of the relationship, right? We said the roots of this system for the underdamped system were given by a real part and an imaginary part, right? So the real part was the product of the natural frequency and the damping ratio, and the imaginary part was this thing, right? Omega n times square root of 1 minus zeta squared. So what's interesting about this is actually, if we consider, let's consider maybe how does the damping ratio relate if we wanted to look at a plot of the real imaginary axis, okay? And we wanted to look at where could these roots be. So what I want to consider is, let's consider a line that originates from the origin, goes up and down like this, and both of these have an angle theta, right? Or I guess technically this is, I guess, minus theta, right? Let's consider root locations, these R1 and R2. What if they're lying along these green lines, okay? What is going to happen in that case? Okay, so I don't know. Let's take one of these for example. Let me erase this. Let's take this far one. It's probably the easier one to stare at. Okay, yeah, and you know what? Let's look at one of them. How about? Okay, let's look at this one up here. Okay, so this guy right here has got a real component here, which is sigma, and it has an imaginary component, like we said over here, which is omega d, right? So this angle, I think everyone would agree that the angle theta, right? We could say that tangent of theta is basically what? It's opposite over adjacent. So it's the opposite. So this is what? It's omega d all over sigma, right? Would everyone agree that's the same thing? Okay, so what was omega d? Omega d was omega n square root of 1 minus zeta squared. And then what was sigma? Sigma was zeta omega n. So look at this, the omega n's cancel, and then aha, look at this. This is kind of interesting. Again, we see that this is only a function of the damping ratio. So in other words, theta is just the inverse tangent of square root of 1 minus zeta squared all over zeta, right? The other way you could interpret this is basically everything along this line has the exact same damping ratio zeta, right? So it doesn't matter if you're here or here or here or anywhere along these green lines, as long as you make the same angle from the real axis, you're gonna have the exact same damping ratio. So for example, right, let's go back to this 1 over square root 2, right? This damping ratio of 0.707. Right? So you could think about this, and if you plug that into this expression, you're going to see, okay, theta has got to basically be tangent inverse of square root of 1 minus 0.707 squared all over 0.707. I think you work this thing out, this comes out to actually exactly 45 degrees, okay? So what this is telling us here is that if you want your system to have a damping ratio of 0.707, you better make sure that the root is along a line which is 45 degrees off of the real axis. Okay, so that's kind of fascinating. Okay, let me erase the board and we'll look at how about natural frequency next. All right, so now let's look at natural frequency. So instead of considering a line originating from the origin and heading out at a constant angle, what if we consider a circle with center at the origin and radius, I don't know, let's call this radius r or something like that. So again, I think you would agree that, all right, if you had one of the roots at these locations along this circle, again, it would have a real component, which was sigma, and it would have an imaginary component, which was omega d. Right? So I think everyone would agree from geometry, right, that r, right, it's just Pythagorean theorem of this thing, right? It's sigma squared plus omega d squared square rooted, right? Okay, so just jam in all of our definitions. So this is now sigma or zeta omega n, this quantity squared, plus the omega n square root of 1 minus zeta squared quantity squared, and then square root this whole thing. Okay, so again, let's just work this guy out a little bit. Oh boy, okay, so this is what, zeta squared omega n squared plus omega n squared times 1 minus zeta squared. Yeah, all of this thing square rooted. Right? Okay, so yeah, okay, let's work this out again. Zeta squared omega n squared plus omega n squared minus omega n squared zeta squared. Okay, there we go. So this cancels with this, and we end up with, this actually comes out pretty darn beautiful, omega n. So the radius is just omega n. So interesting, again, we see that basically any pole, or sorry, any root location which is along a radius, here, this radius is just the natural frequency. So basically, the farther away you are from the origin, the farther away you are from the origin, the larger the natural frequency of the system is. And anything along a circle has the exact same natural frequency, right? All right, so the last one to consider, which is actually almost kind of trivial, is let's look at a constant line, either here or here, which is a distance, well, I guess the distance is omega d. Away from the real axis. And again, like I said, I think this is trivial to see because you can pretty much observe right off the bat here that any pole that is along these horizontal lines has the exact same damped natural frequency. So I don't even think there's a need to write that down because I think it's pretty obvious. So the farther away you are from the from this real line, right? So if you move up or down vertically, that increases the damped natural frequency of your system, right? So maybe what's interesting is maybe we should summarize and kind of draw this in a larger picture, right? So we see that basically the natural frequency and the damping ratio have a relationship with the root location. So again, we saw that things along a line like this with a constant angle theta, these have the same damping ratio, right? And then what we also saw was that things along a radius of radius r, or I guess this radius was basically the natural frequency, right? All of these things have the same natural frequency, right? And finally, the last thing that we saw is that the things that are along, this pen is on the way out, right? Things that are along a horizontal line, these things all have the distance from the real axis of omega d, and these all have the same omega d. So it's actually fascinating that you can start thinking about maybe where do these intersect, how if you want to satisfy multiple requirements at the same time, meaning you want a specific damping ratio and you want a specific natural frequency. Sorry, I'm pointing to the wrong thing. Same damped natural frequency. You're going to have to look at where the red and the green intersect and vice versa and yada yada. So again, I think this is interesting that it shows you again why a second order system is so nice, because as soon as you know the damping ratio and the natural frequency, you can start talking about more abstract things like how they relate to the pole locations and how they relate to the response of the system directly, right? Okay, so tell you what, let's take a minute to maybe go over an example of this. All right, so let's look at a real system and see how we can model it using a standard second order differential equation. So here's our example system. It's just your classic pendulum where you've got a large mass down here connected via a massless rod of length L, and all you do with this is we're going to deflect it with some initial condition, some initial angular deflection from vertical, and we're just going to let the thing go, let it basically oscillate. And you can see that it basically has sinusoidal behavior with sort of this exponential decay due to the viscous friction at the pivot point, right? Eventually the thing comes to rest. So all we want to do is let's model this system, write down the equations of motion, and see if we can massage this down into a standard second order differential equation, right? Okay, so again, I've sketched this up here, and I don't want to spend a ton of time going over the modeling because I don't think that's the real effort or the real point of the discussion today. So I'm just going to throw this up. Equations of motion are basically Newton's second law for rotation, right? So we're going to write all of the torques about this pivot point is equal to the moment of inertia times the angular acceleration, right? So j theta double dot of t, right? Okay, so the torques, what do we got here? I think if you stare at this thing long enough, you'll see you've got an mg this way, but then the component which is normal to the rod is sine theta, right? So you end up with a retarding torque of magnitude minus mg and then L, right? mgl sine theta. Right, because the mg sine theta is the force, and then the L is the moment arm. So this is basically the torque due to gravity of the mass, right? Okay, then you have the viscous friction at the pivot. So let's use just a linear viscous coefficient of friction B times theta dot. This is our model of the friction. Okay. That's basically it. So is equal to J. So the moment of inertia for this, for a point mass, a distance L away from the axis of rotation, I think everyone will agree that that is just going to be mL squared, right? Okay, so that's moment of inertia times theta double dot of T. Great. Okay, let's isolate everything on one side and actually, I think here, let's do one more step. Let's move everything to one side so we can write this thing as mL squared theta double dot of T plus B theta dot of T plus mgl sine theta of T is equal to 0, right? And now let's normalize everything by mL squared. So I want to divide everything by mL squared. So basically this is going to go away. Right, this becomes a 1. This is all this over mL squared, and then this is all of this over mL squared. So actually, so this m is going to cancel with this m. This L is going to get one of these L's gone. So I think we're going to end up something like this. Okay, yeah, would everyone agree? So this thing right here is a second order differential equation, right? Now, to write this in standard form, right, I want this thing to look like theta double dot of T plus 2 zeta omega n theta dot of T plus omega n squared theta of T is equal to 0, right? This bottom line, this is the standard second order form. So you see, again, really pretty darn simple. Well, actually, hold on. I take it back. We should be careful. Look at this. You can't make this equal to this right now because the actual differential equation right here, right? This is actually a nonlinear second order differential equation because of this sine theta term, right? You notice this is the only thing that's preventing us from writing this in a standard linear second order differential equation form. So we better write that down. Let's circle this equation because this is the actual equations of motion that we may want to think about simulating later. But it is nonlinear, right? So this is a nonlinear second order ODE, right? Okay, so in order to get it down to this format, we're gonna have to make a couple of approximations. So let's go ahead and apply like a small angle approximation. And remember, this here is where we are sort of diverging from I guess if you want to call this the truth, right? We're going to start making some approximations in order to get it into linear form. So if we assume that the angles that this thing is swinging through are small, then we can basically make the argument that what sine theta, this is about theta, right? Would everyone agree? Okay, in that case, this differential equation in red, right, this becomes theta double dot of T plus B over mL squared theta dot of T plus G over L theta of T is equal to 0. Now, this thing, we can make it look like the standard second order differential equation by basically just matching coefficients, right? So I want G over L to equal omega n squared, right? So this is the coefficient of theta of T, right? I got to make the coefficient of theta here equal the coefficient of theta here, right? And then I got to make the coefficient of theta dot, I need b over ml squared has got to equal the coefficient of theta dot, right? It's got to equal 2 zeta omega n, right? So this is the coefficient of theta dot of t, right? Okay, so 2 equations, 2 unknowns, just solve this thing for zeta and omega n, and basically what you'll end up with is that the natural frequency of this standard form is square root of g over L, and then the damping ratio is b all over the quantity 2m L to the 3/2 square root of g. Okay, so great. We basically have this pendulum system. Again, we got to be a little bit careful. We have the small angle pendulum system written as a standard second order differential equation with this natural frequency and this damping ratio, right? So this is kind of interesting because you can actually kind of think about this from multiple perspectives. So one perspective is you could say, okay, let's pretend I know what gravity is. I think you probably do, right? 9.81, that seems like a reasonable number. How about L? You probably can get L, right, on this pendulum pretty easily. Just measure this distance, right? That's pretty easy. Well, how about the mass? Yeah, sure, you could probably measure the mass of that. Again, put the mass on a scale. Now, this is where it gets interesting. This term B, right? This is our viscous coefficient of friction here. Measuring this directly is a little bit tricky here. So you may want to ask yourself, is there a way that I could experimentally try to measure the pendulum angle and back out what this value of B should be? Well, actually, yeah, you can totally do that using some of our discussion previously. So if you remember, let me erase this so I get a little bit more white space on the board, okay? So our goal right now here is we want to find B experimentally. Okay, so if you remember previously, we said that the idea with a second order differential equation is if this thing was a second order differential equation, we expect it to look something like this, right? It's this decaying sinusoidal term, and we talked about this decrement ratio where if you take any 2 points which are 1 period apart and look at their ratio, that it's this decrement ratio eta, right? So this eta is basically, we said it's the thing at a time t plus the period all over x of t. Right? This is the ratio. So we said the easiest thing to do is probably pick like maximas or minimas. Those are nice, easy points to pick off on this graph, right? So just find this maximum here, find this maximum here, and you basically just measure the ratio of the 2 heights, right? So here is the height of, this is x at t there, and then this one here is x of t plus the period, plus capital T, right? That's all we're going to do, right? So what I'm getting at is it's actually easy to get this eta value experimentally, right? You would hook up a sensor to the pendulum, watch this thing spin around. Once you get this trace of the pendulum motion, just go ahead and find 2 successive maximas and basically compute this ratio, right? So what I'm getting at is you can get this experimentally. Maybe I'll say eta exp for eta experimental, right? You can obtain this value, right? Okay, now what we said is if this thing was a second order system, we claimed that this eta, you remember previously, that eta is only a function of the damping ratio, right? This is theoretically, it's e to the minus 2 pi zeta all over square root of 1 minus zeta squared, right? So you know what? You could actually flip this backwards, right? You could solve this expression for eta, or sorry, solve it for zeta in terms of eta. Whoops, that's kind of an odd terminology here, rhyming terminology. But anyway, let me do that. So you could get basically the damping ratio. If you solve that, you basically get this thing to be negative natural log of eta all over square root of 4 pi squared plus natural log of eta squared. Okay, so what's great is the second you have this eta obtained via experiment, you basically can plug it into this expression and then you get basically the damping ratio that is measured experimentally. And then if you look, this is theoretically our model of what the damping ratio should be if the system behaves as this standard second order differential equation. So look at this. You can basically just solve for for B here, right? Because again, we said you can measure the mass, the length, and the gravity. Those are all pretty easy, right? So at the end of the day, what we end up with is you could obtain beta experimentally by just, again, solving for B here, right? So that is just what B is, 2 times zeta ml to the 3/2 times square root of G, right? Right? So this is actually pretty interesting. So what we ended up with is, starting with this system, we basically derived a nonlinear differential equation here. So maybe what we should do is now let's run over to MATLAB Simulink and simulate the nonlinear system. So there's a couple things we should do. We should build a model which represents this nonlinear differential equation, which is sort of our quote-unquote high fidelity model, which should model this pendulum at large, even at large angles, right? Even upside down, this equation should be valid, right? Then what we did is we made an approximation and said, okay, if we restrict the motion to small angles, we could come up with a linear differential equation, which can be written in standard second order form. And then we even came up with a way of now measuring parameters from the system response, such as finding out what the viscous coefficient for this model was via experiment. So what we want to do is let's run a virtual experiment in Simulink where we're going to build a model of both the nonlinear system and the linear system and see how well do all of our predictions pan out, okay? So for giggles, let's go ahead and use some constants. I think in the simulation I use a constant, a mass of 1, a viscous damping coefficient of 0.1, a length of 0.5, and then obviously gravity of 9.81. Okay, so that's a game plan. So let's jump over to Simulink and see how does this system behave.
All right, so here we are. So I've built 2 Simulink models. So you can see this top Simulink model is basically representing the nonlinear differential equation. You can see here the sine theta term right here. And then down below, I've got a linear version of it, which is basically the exact same model, but you'll notice it's just missing that sine term here because we small angle approximated that thing away and just said that we were just going to use theta instead of sine theta. So again, here's our 2 models of those 2 ordinary differential equations. Again, if you would like a little bit of a refresher of how to use Simulink to solve ordinary differential equations, please feel free to check out this video here where we talk about it extensively. And in fact, we have a sister video to that which also talks about how to interact with a Simulink model like this through a MATLAB script. And that's exactly what I would like to do next. I would like to basically define all of these parameters like M, G, L, as well as the initial condition here, which is the initial deflection angle of both of these models. So let's do that in a MATLAB script. So that's exactly what I've done right over here. So here's my MATLAB script. I've gone ahead and here's the constants we talked about. And as we said, we can now that we have these constants, we can go ahead and compute what the natural frequency and the damping ratio of this system should be. And actually, you know, for giggles, I also compute the damped natural frequency just to see what it should oscillate about, what frequency it should oscillate. And we should be very careful. This should be the frequency of oscillation of the linear system, right? Because all of this thing, the idea of damping ratio, natural frequency, damped natural frequency, these are all linear ideas, right? So the nonlinear system doesn't have to behave according to these parameters at all, only the linear system. Okay, so let's move on. Initial conditions. Let's start with an initial condition which makes the small angle approximation valid. So I think 2 degrees is a very small angle, so things should work. So what I'm going to do here is I'm going to simulate the model, and then I want to just basically plot the response of the nonlinear theta as well as the linear theta. So I just want to see how do these 2 pendulums swing relative to one another, okay? So let's go ahead and run this guy. And let me bring over the plot. And there are 2 signals in this. They are just overlapping. And again, that's because we have a small angle. I mean, if we zoom in on here, you might be able to see some small differences. Yeah, okay, now you're seeing some differences, but it's not very much. And again, this is because the small angle approximation is valid, and therefore our calculation of damping ratio and natural frequency match very well in the sense that the linear model matches the nonlinear model very well. Now, you'll notice I have this, it might be a little hard to see in the screen capture, but I have these two little symbols. I got a triangle here and a plus sign here. What I'm doing is I'm in the script, maybe we can quickly take a gander at it. I don't think it's worth looking at it a ton, but I'm basically looking for two successive maximums, and then I'm plotting those. So in fact, you know what, maybe let's make these things a little bit bigger just so they're easier to see. Let's do something like this. That way, I think you could see the actual marks a little bit easier. Let me run this guy again. Okay, there you go. So I basically want these two so I can calculate that eta ratio that we were talking about earlier, okay? So that's what I did right here. Here's eta, right? It's just the ratio of the two peaks. Now, make a note here that I'm actually using the nonlinear theta value to calculate the angle, because if you think about this, if we were to do this experimentally and actually swing a real pendulum, right, the real pendulum is non-linear, right? It's actually got tons of other effects that we didn't even model in our system. So the closest I can get to that in Simulink is by using the non-linear measurement, not the linear measurement, right? So I calculate eta, or the decrement ratio, based on the non-linear position of the pendulum, and therefore I go through just like we talked about on the board. I can then go ahead and calculate a damping ratio that is measured experimentally, and therefore calculate a viscous damping coefficient that is experimentally determined. And what I'm doing over here is I'm comparing the two. So here's the actual value. Again, actual means the linear model's damping ratio, and here is the damping ratio we obtain if we measure the nonlinear response. And you can see these two things are exactly the same, or at least the same up to 4 digits of precision. And again, that's because we have such a small deflection angle that it really doesn't make much of a difference. The nonlinear and the linear model behave the same. Now, that story might change if we had a larger deflection. I don't know, how about instead of 2 degrees, let's make it 20 degrees of deflection, okay? So now maybe it's not actually so small an angle any longer. So if I run this model again, you can start to see there are some differences, but still the linear model matches quite well with the nonlinear model, and as such, we still get a reasonable, actually a very reasonable match between the damping ratios and the viscous damping coefficients. Basically, the model parameters of the linear system match what the, or predict very well what the nonlinear system does. Now, this starts to deteriorate if we start increasing this number. I don't know, how about 80 degrees of deflection, right? I don't think this is such a small angle any longer. So if I run this model again, now you start seeing some real differences, right? And again, notice that the period of oscillation is not the same, right? The nonlinear system actually appears to have a longer period of oscillation. In fact, this blue line is not necessarily even a sinusoid. It looks like a sinusoid, but it's probably something much more complex, right? Because the differential equation is nonlinear. I mean, even the linear differential equation, technically, it is an underlying pure sinusoid, but it also has that exponential decay on it. So again, if we're measuring the nonlinear response, right, the blue, and using that to calculate our damping ratio, you can start to see that we start to get some divergence here, and we get some errors building up from the fact that we are trying to fit a linear model using the response of a nonlinear system, right? Now, here's where it gets actually really interesting. What if I do something like this? How about this initial condition? What does this mean, 170 degrees? If you think about this long enough, what we're doing to the pendulum is we are turning it all the way up. And actually, you know what's actually even more interesting? Let's make it more than vertical. Let's go 190 degrees. So this is we started at the bottom, and now we are rotating counterclockwise past vertical. So the pendulum actually starts 10 degrees past vertical. Now, before I hit run, ask yourself in your head, what would a real pendulum do if it was cranked all the way up past vertical and then I let it go, right? Let's run this and you tell me which one seems more reasonable. So I'm going to run this again, and well, this is interesting. Look at this behavior. What does the blue trace do? Again, the blue is the nonlinear system. So we started at 190 degrees of deflection, and look at this. It decides it's going to go down and oscillate and settle out around 360 degrees. So actually, if you think about this long enough, this is the right behavior. This is the correct behavior of what you would expect a real nonlinear pendulum to do, right? You cranked it all the way up past vertical, so it's actually going to fall down kind of in the other direction, right? And it's going to oscillate around 360 degrees of deflection, not around 0. Look at what the linear model predicts, and this is why linear models are not good when you move far away from the operating point, right? So in this case, it claims, the linear model says, okay, I'm going to start out here at 190 degrees, and somehow it's going to magically swing back to 0 degrees when we let it go. So again, this is clear garbage, right? This doesn't make a lot of sense. This linear model doesn't make sense. So again, you just got to be careful of how you're simulating these systems. But I think that's a slight tangent. I just get excited about this kind of stuff because you can see how a nonlinear model, right, captures all of this very interesting behavior, and you can start thinking about how you can model very complicated systems using nonlinear ordinary differential equations. The reason I say it's a tangent because today what we really wanted to talk about was linear second order models down here and how we can write them in standard form. And I hope we've convinced you now that second order linear differential equations are fully characterized by these two parameters, right? The damping ratio and the natural frequency. And they tell you everything you pretty much need to know about the system and its behavior. So, with that being said, I think this is a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button or hit the like, it really does help the channel and help us continue making these videos. And remember, the new videos come out every Monday, so hopefully I will catch you at one of these future discussions and we can all learn something new together. So, until we talk again, I think I'm going to sign off for now. Talk to you later. Bye.